Hello and welcome to first day of circuit analysis series. In today's discussion, we're going to go over current, voltage, resistance, and power. Alright, let's get started. So current I has units of amperes or amps, which is equivalent to coulombs per second, where coulombs is the unit of charge. And the simplified definition of current is charge in motion. So looking at the definition, we know that we need to understand the behavior of charge in circuits in order to understand current. And from our physics course, you might remember that the charge that each electron carries is equal to a negative 1.6 times 10 to the negative 19 coulombs, and it's a constant value, it doesn't change. Now let's assume I have this simple conductor circuit with no elements attached to it, and for some reason I have this one electron circling my circuit every second, and I want to know what my current is here. So I'm going to attach a measurement device, and this is an ammeter, and it tells me what my current is. So what is my measured value of current going to be? Well, we said current is rate of charge passing through this device. So I have one electron passing through this device every second, and the charge that it carries is negative 1.6 times 10 to the negative 19 coulombs. And we said that it's a rate, so it's every second. So it's negative 1.6 times 10 to the negative 19 amps. And one more thing that's noticeable over here is this negative sign in front of this current. So I'm going to take that off, and I'm going to say current is just 1.6 times 10 to the negative 19 amps, except I'm just going to reverse the direction of current here. So my electron had a direction of clockwise circling in our circuit, and I'm just going to assume that my current has a direction of counterclockwise here. And going forward, we're always going to assume that current travels opposite the direction of electrons. So the question is, why did that single electron in our circuit move at all? What excited this electron to move? And the answer to that is simplified by energy band diagrams. Now, energy band diagrams consist of two bands. First band is a valence band, which represents all electrons within a material that are there to connect the atoms together and form the structure of that material. And the second band, conduction band, represents all the localized electrons from valence band that are free to move. So we're going to provide some energy to the valence band electrons, move them here, and now they're delocalized and they can move and conduct electricity. Let's now compare the energy band diagrams of insulators, semiconductors, and conductors. So we know that insulators are not a good source of conduction, and their energy band diagram looks something like this, where there is a large gap between the energy level of conduction band and valence band. Large gap. So notice the vertical axis is energy. So this says that this gap is a large energy difference between these two bands. So with insulators, it is very difficult to conduct electricity. I will need to provide a very large amount of energy to the valence band electrons to knock them to the conduction band and have the localized electrons free to move. And large energy might damage the equipment. And for semiconductors, the diagram looks something like this, where the gap is much more smaller, energy is also much more smaller, so with the right amount of energy we can get electrons from the valence band to the conduction band ready to move around. Now for conductors, the conduction band and the valence band overlap, and this means that for conductors it is very easy to get electrons from the valence band to the conduction band and have them move in the opposite direction of our electric field and create current. What is this energy source that provides energy to the valence band electrons, knocks them to the conduction band, and creates free moving electrons? In circuits, this is done by EMFs, electromotive forces. And examples of EMFs are batteries, generators, and power supplies. So one thing to know about EMFs right now is that EMFs, say this is an EMF, they have a positive and a negative terminal. So when I connect this EMF to a circuit, let's say the circuit is somewhere and we don't care about it, but there's going to be electrons created from the negative side moving towards the positive side. And we said that because of that, we're going to have the current in the opposite direction. So my current is going to go from the positive and it's going to come back to the negative. And this current is basically a whole bunch of electrons, or in the opposite direction. And these charges, electrons, are going to gain a potential energy difference of delta E when they pass through this EMF. Now I'm going to connect that EMF to the first circuit that we analyzed before. Now this time, instead of one electron circling my circuit, I'm going to have a lot of them. And I'm just going to denote their charge value, their overall charge value, with the letter Q. So Q is total charge generated since time equal to 0. And time equals to 0 is when we connect this EMF to the circuit. And if you want to calculate Q and you have the information, it's just number of electrons generated times the charge of each electron. So let's say my QT graph looks something like this, where at time equals to 0, my EMF starts generating charge at a constant rate. Why do I say constant rate? Because it's linear graph, it's increasing linearly. So I also know that I'm going to have a current going opposite direction of my electrons. So I'm going to place an ammeter again, and I want to know my current. And we said that current is the rate of charge, right? So what is the rate of charge? Well, rate of this graph is just its slope. And since it's linear, my slope is constant everywhere. So from your high school math class, you might remember that the equation for slope is y2 minus y1 over x2 minus x1. So I'm just gonna, since my slope is constant, I'm just gonna choose two arbitrary points, and I'm gonna calculate or measure how much current has been generated within that time. So this is Q1, Q2. So I'm gonna call Q2 minus Q1 a delta Q and T2 minus T1 a delta T. So my current is gonna be delta Q over delta T here. And because my slope is constant, it doesn't matter where I calculate it. So you might ask, what if my QT graph wasn't linear? Well, how would you calculate current then? What if my QT was something like this? What if it was something like this? Then I know that my current changes also. Now I have a time-dependent current. So it's a function of time. And what I call a time-dependent current, an instantaneous current. Instantaneous current. So how are we going to go about getting an equation for this time-dependent current function? From your calculus course, you might remember that if you take the limit as time approaches 0 of a slope, which in this case is our current, then you will get the derivative of that value. So here I'm saying that my instantaneous current is the instantaneous slope of my graph. So if I want to calculate my current at time, let's say time A, I'm going to take the derivative of my QT at time A, which is going to give me this instantaneous slope over here, and that's going to be my I of A. Same thing with point B. So let's say my instantaneous slope at point B is, looks something like that. So my IB is going to be the value of that slope over there. And it makes sense, right? Because derivative is also a rate, derivative of time. So can I use this derivative with the same constant slope graph as well? Yes, derivative is, again, same thing as slope. So with the same equation, I'm gonna derive another one. I'm gonna multiply both sides by dt, and that's gonna give me dq is equal to it dt. Now I'm going to integrate both sides from 0 to t, and this is going to give me that qt is equal to integral from 0 to t it dt with an initial condition, which we said that at time 0 we're connecting the EMF, nothing has happened. For now we're just going to assume this is 0. And what this means is that if I were given a current time graph instead of charge time, then let's say it looks something like this. It doesn't matter how it looks, whatever. It says that if I want to calculate how much current is generated by this EMF within two different time values, A and B, all I gotta do is integrate my function of I and calculate this area under the curve. So my Q of A to B is equal to integral A to B of my IT dt. So what it's saying is that the opposite is also calculable. Earlier I said that it is EMFs that provides the energy to a circuit and creates current. But in reality, it is not energy provided to a circuit, it is voltage, it is potential that is provided to the circuit. So let's analyze voltage to understand it. So voltage, V or E, has units of volts, which is equivalent to joules per coulomb. Now notice the difference between volts and just energy, which is joules. So voltage says that if I have a 1 volt voltage supply, it's going to provide the circuit 1 joules of energy per each coulomb of charge that goes through it. So what does that mean? That means that if I connect a 1 volt power supply to two circuits, so I have circuit number 1 and just a box, black box. We don't know what's inside the black box. All we know is that we watch over these circuits for 1 minute, and all we see is that an overall charge of 1 coulomb going through this circuit number 1 back into the circuit, and for circuit number 2 it's 10 coulombs. So again, it's the same voltage source, 1 volts, and we want to know how much energy this same voltage source provided to these two circuits. So here we know that 1 volt is equal to X joules over 1 coulomb. So we know that our voltage source provided 1 joules of energy to this charge or to the circuit number 1, whereas to circuit number 2, 1 volt is equal to X joules over 10 coulombs. So the same voltage source provided 10 times more energy to circuit number 2. And what this is saying is that circuit characteristics matter too. Voltage source alone can't tell you how much current will be created in a circuit once you connect to it. You need to know the characteristics of the circuit. So what is the characteristics of circuit number 1 that's different from circuit number 2? As we're going to go over very soon, it's resistance. So circuit number 1 had a high resistance, and that resulted in very small amount of charge generated from this voltage source to the circuit, whereas circuit number 2 had much more smaller resistance, and that resulted in a lot of current, in a lot of charges generated from the voltage source and back to the circuit, and more energy was provided to the circuit as well. So that's good enough for now. Let's just define voltage now. So I'm not going to write the entire thing, but voltage is just potential difference across terminals of elements that either deliver or consume energy. So it's first of all saying a voltage is a potential difference. So let's see what that means. I have the EMF, and let's say it has a 10 volt rating, And again, we said that it has a positive and a negative terminal. So I'm going to call these terminals V2 and V1. So I know that my V2 is equal to V1, the potential at V1 plus the extra potential that I provided to it. And I will rewrite by saying that 10 volts is equal to V2 minus V1 is equal to delta V. Now this is what the definition means by saying that voltage is a potential difference. It's a potential difference provided to two terminals. And the second part of the definition says that either consumes, that the components are either consume or deliver. So the definition is saying not only components that generate energy can have voltage rating, but the ones that also consume energy can also have voltage rating. So let's say I know this one is definitely a supply source, and I'm going to connect it to a load. Say it's a lamp or whatever, consumes energy. So I know that these two guys share terminals together. So then this load must also have a same potential difference across it. And if it has a potential difference, then it must also have terminals, positive and negative. But how do I put the positive negative? Is it this way or is it this way? Well, that's the important part that differentiates loads from sources. So I know that my supply, I know that this guy is a supply, right? And we also discussed that when I connect to the circuit, it's going to generate a current going from this direction to this direction. So my current is going to gain a 10 volt energy when it passes through it, right? But my load current must lose energy when it passes through it. So when my I goes from here to here, it loses energy and then goes out. So then my terminals must be opposite the direction. So my current must go in the positive terminal first and then get out from the negative to lose this 10 volts of energy. And then back in the supply and so on. So as far as the types of voltage sources that we have, first one is a DC voltage source, and it's saying that we have a constant value of X that is provided over time and it doesn't change. So if I had a function of time for this graph, it would be same as X volts. Why? Because it does not change over time. It doesn't have time dependence. It's just a constant. And the second type is alternating current types. Alternating current voltage sources, AC voltage sources, have alternating patterns. And the one that we're going to be dealing with is this sinusoidal one, which is famous as AC current. And we're going to analyze the differences later, but for now know that energy can be transferred to a circuit in different methods, either through a DC source or an AC source. These voltage supplies can provide energy, joules per coulomb, to the circuit. There's also one more type of voltage source, and it's a variable voltage source, and it can be anything. It doesn't have any patterns, and we're not gonna go over that right now. Now I'm gonna connect my voltage source delta V to these two loads, and I'm gonna have a current going from the voltage source to the first load, emptying out a little bit of energy, consuming, and out of this first load to the second load, and then consume the rest of the energy and back to the voltage source. Because these two guys are sharing terminals, their overall voltage rating must match the voltage rating of the source as well. But I also know that these guys have individual terminals too, so they must have potential differences separate from each other. And my goal over here is to create an equation connecting the generated potential energy to consumed potential energy. And from my energy conservation, I know that generated energy in a circuit, in a confined circuit here, must equal to energy consumed. And if I have multiple loads consuming, then the accumulated value of the consumed energy must equal to the generated one. And I also know that my current must be the same everywhere. So if I name this I1, I2, and I3, my I1 must equal to I2 must equal to I3. Why? Because there is no alternative path for current to take and escape. So current same everywhere here, and because of that there is no charge escaping my circuit. I'm just gonna say Q1 to Q2, but what I mean is that there's no charge escaping. So my energy in joules is conserved, my charge in coulombs is conserved, then this must mean that my voltage, which is in joules per coulomb, must also be conserved here. So then I can say that delta V is equal to delta V1 plus delta V2. So each one of these loads consume a little bit of potential energy, and combined it must equal to the potential energy of the source. I talked about characteristics of a circuit a little bit, and I said the characteristics is the resistance of the circuit. So with a high resistive circuit, if I connect a voltage source to it, it's going to result in small amount of current. And if the resistance of the circuit is very small, then I connect the same voltage source to it, my current is going to be much larger. So let's learn more about the resistance now. So resistance R has units of ohms. And the simple definition of it is R resists movement of charge. So I know that if I have a higher voltage source, I will have higher current. Is that true? Yes, because there's going to be more energy provided to my circuit. I also know that if I have a small resistance, I will also have a high current. So it looks like the relationship between current and resistance is indirectly proportional. And with this, I'm going to write a relationship between these three, which is voltage over resistance of the circuit is equal to the current. And this is known as Ohm's Law. Now, using Ohm's Law, given two information, we can calculate the third. If we have V and R, we can calculate I. If we have I and R, we can calculate V. And if we have V and I, we can calculate R. So let's analyze this circuit. Let's say this circuit tells me that, hey, this load has a resistance of 10 ohms. So I'm given that information. I also know that the terminals across it has 10 volts potential difference. So what is my current gonna be here? Well, my current is gonna be using Ohm's law. It's gonna be 10 volts over 10 ohms is equal to 1 amps. And my 1 amps is gonna be the same everywhere. So I'm gonna have 1 amp in that direction, 1 amp in this direction. This is my current. And now it's time for power. So let's understand power from the definition. So power is rate of energy transfer. And notice it's transfer, it's not consume or generate, it can be both. So if it's rate, again we said rate is time, right? So rate of energy, then it's joules per second, right? And in circuits we call that watts. So given the three components, voltage, current, and resistance, how can we derive an equation for power? So let's say my voltage has units of joules per coulombs, and my current has units of coulombs per second. So if I cross the coulombs, I do have my equation here, joules per second is equal to watts. So power is equal to voltage times current. And I will replace voltage with my Ohm's law, and that's going to give me IR times I is equal to I squared R. And again, I'm going to replace the I this time, times V over R is equal to V squared over R. So I have these three equations that I used Ohm's law for to get an equation for power. So let's analyze this circuit and how much power is being generated versus how much power is being consumed. So from the previous example, we know that we have 1 amps of current in this circuit. How it's I is equal to 10 volts over 10 ohms is equal to 1 amps. So what is the power of my generation? So power generated is equal to VI. VI is equal to 10 times 1 is equal to 10 watts. What is my power consumed? I have to use the resistance now. Now I know the power is equal to I squared R is equal to 1 squared times 10 is equal to 10 watts. So see how these two are equal together, and that's why energy conservation in circuits is also valid. So before I finish the lecture today, I want you to know that when I've been writing equations such as the following, I've been saying like V over R is equal to I. This is for DC, direct current, because in DC, IT is the same everywhere, so we said we're gonna call that an I, so no dependency on time. But this Ohm's law and the power equations also are true for time dependent. It doesn't matter if it's AC or variable, my Ohm's law still stands. Or power time is equal to voltage time times IT. So let's say if I have a voltage source that looks something like this. It starts from 10 volts and does this. And let's say I want to find what my current is given my resistance is 10 ohms. So I can still use Ohm's law, and I can say I is equal to V over R. So I can choose a couple of points on this graph and divide it by resistance, which is 10 ohms, and get the following. That my current looks exactly the same as my voltage, except that it starts at 1 amps now. So all these points, I just divided them by 10, whatever the value was, starting from 10 volts. And they resulted in a similar looking graph, except with different values now. And again, I can use the same for my power. So I can say my PT is equal to IT VT. And this should have been IT is equal to ET over R. R is always constant. Remember that unless it is specified that it changes for because of a factor, it remains the same in circuits. So R is a straight line. So now let's do power. So I'm going to take the same 2 points from the current, and I'm going to multiply to the voltage. So I'm going to multiply. And this time the graph will look same, except that the minima and the maxima will be a little bit intensified. So let me redraw this for better visualization. So it will look something like this. Have an intensified maxima, an intensified minima, and then back at where it was. And it's gonna start at 10 times 1 at 10 watts. So all these points correspond to these multiplications. And one more important thing is that notice how the graph of voltage dictated how the current and power will look. And this is very important because this tells us that in the future circuits, whatever source the voltage is, whether it's an AC or DC, that's going to tell us how the responses of circuit components to this voltage source are going to be. And lastly, just like how we said that from charge time graph I can calculate current, the same way I can use my energy time graph and just take the derivative at any point. I'm not going to drive that again. If you want to know how, you can go back to the current section and look at the limit derivation. But basically my power PT will be the derivative of my energy time graph. So power at time A will be the instantaneous slope, and power at point B will be the instantaneous slope over here. And again, just like current, we can drive the opposite. We can say if I have the power graph, doesn't matter how it looks, I can integrate my power to get energy. So ET is equal to 0 to T PT dt plus initial condition if you're given by the question. So if I'm given the power graph, I can take 2 points, A and B, and I can calculate how much energy was generated or consumed between these 2 points by integrating from A to B of my power curve. So I'm placing all these equations in one place, so you can go ahead and pause the video and look at each one of them. For the one with the resistance, that one is for the resistance video, so do watch the shorter video that I'm uploading after this. Those are bases for our next lectures.